I am Prabhavathy, Assistant Professor, Department of Mathematics, A.D.M College for Women, Nagapattinam. I already presented a module 1 regarding prime numbers, composite numbers. In this module, let us explain about distribution of primes. First, we will recall about prime numbers. Prime numbers are natural numbers which are positive, which have only two divisors, 1 and itself. Now we will see some facts about prime numbers. There are infinity of prime numbers and the set is a proper subset of the set of all natural numbers. What more is known about the structure of the set of primes, how they are distributed or scattered among the natural numbers? There is no definite answer to these questions. There is no formula to enumerate all the primes. Also, there is no recurrence formula connecting the nth prime with the n minus 1th prime or the n plus 1th prime. There are many interesting oddities in the set of primes. For example, the primes 2 and 3 are consecutive integers. Next, there is a single gap between the consecutive primes 3, 5, 7. But there is no rule for a gap of definite size between consecutive integers. We can have consecutive primes with any desired gap between them. Thus, there is a mess about the distribution of primes. In absence of definite rules for getting all the primes, there are volumes of guesses and conjectures about the distribution of primes. Of course, with certain limitations or constraints. Some of them have been proved and some of them have been disproved, and many have no answers. Verification confirms in some cases and evades in some other cases. We discuss here some of the conjectures and results about the distribution of primes. First conjecture, if n greater than 1 is a natural number, then between n and 2n there is at least one prime number. If n greater than 5, there are at least two prime numbers between n and 2n. These two conjectures were proved by Sierpinski in the year 1930. Third conjecture, there is at least one prime number between n square and n plus 1 the whole square for any natural number n. An improved version of the above conjecture is that there is at least one prime number between n square and n square plus n. If n greater than 2 is a natural number, then there is at least one prime number between n and n factorial. Arrange the natural numbers in a triangular form as below. That is, in first row 1, in second row 2, 3, in third row third elements 4, 5, 6. Like this, if we arrange the numbers, natural numbers in a triangular form, we can observe that in first row, some authors assume that one is a prime numbers and some others assume that one is a neither prime nor composite. In the second row, there are two prime numbers, 2 and 3. In third row, only one prime, 5. So similarly, if we observe in each row, the nth row contains n numbers, which is conjectured that each row contains at least one prime. If n square natural numbers are there, if they are arranged successfully in n rows and n columns like above, then each row or column contains at least one prime. No general proof is available for this conjecture. However, this result has been verified and it is found correct up to the natural number n is equal to 4500. Consecutive primes satisfy different possibilities. It has been proved by many authors that there are infinity of primes Pn such that Pn greater than Pn minus 1 plus Pn plus 1 divided by 2. Here, this Pn is the nth prime and n minus 1 is the Pn minus 1 is the n minus 1th prime and Pn plus 1 is the n plus 1th prime. So further, this conjecture is modified and there is infinity of primes such that the nth prime can be represented in terms of n minus 1th prime and n plus 1th prime. That is, Pn is equal to Pn minus 1 plus Pn plus 1 divided by 2. Second one, Pn square, that is square of nth term, will be greater than product of Pn minus 1 and Pn plus 1. And third conjecture is Pn square will be less than Pn minus 1 into Pn plus 1. So, as I said above, these three will be proved or disproved We don't know, but they are giving some conjectures, some statements. Ninth one, there are infinitely many primes of the form n square plus k, n cube plus 1, n cube plus 2, n cube minus 2, where n is any natural numbers. 10th one, there are infinitely many primes of the form x square plus y square, x square plus y square plus 1, where x and y are natural numbers. So the famous mathematician, the number theorist Fermat, he conjectured that an integer of the form 2 power n plus 1 is a prime number for every integer n greater than or equal to 0. That is every natural number n. But Euler, the famous mathematician, disproved the Fermat's claim by showing that this given number 2 power n plus 1 need not be a prime number. For example, he proved this for n equal to 5. F5 is a composite number. And 12th, the Mersenne conjectured that 2 power p minus 1 is a prime number whenever p is a prime number. It also disproved by giving counter examples. And 13th, Shirk conjectured some properties of nth primes, which is given as p2n, that is 2nth prime. P is denoted by 1 plus or minus p1 plus or minus p2 and so on, plus or minus 2n minus 2 plus or minus p2n minus 1. And p2n plus 1 is given by the relation 1 plus or minus p1 plus or minus p2 plus or minus p2n minus 1 plus or minus 2 into p2n for suitably chosen the signs plus or minus anything. We will see another famous conjecture given by Dirichlet. Dirichlet conjecture and it is proved that any arithmetic progression of the integers contained infinitely many primes. That is, there are infinitely many primes of the form an plus b, where a and b are integers. N is a natural number. So now we will see how Euler disproved the Fermat's conjecture in detail. So now the integer fn is equal to 2 power n plus 1 is a prime for all n greater than or equal to 0 is given by Fermat. This conjecture is made around the year 1660 and we can observe that fn, if we substitute n equal to 0, this fn becomes f0, which is equal to 2 power 0, anything power 0 is 1. So 2 power 1 plus 1, that is 3. If n is equal to 1, f1 is 2 power 1, that is 2 square plus 1, 5. And n is equal to 2. f2 is 2 power 2, that is 2 power 4 plus 1, 17. So similarly, if n is equal to 3, f3 will be 2 power 8 plus 1, that is 257. If n is equal to 4, f4 is 65,537. So we can observe that this f0, f1, f2 are prime numbers. And we can use some other formulas to find out f3 and f4 are prime numbers. And all these numbers are primes and they are follows the Fermat's conjecture. In 1752, Euler proved that this f5, that is 2 power 32 plus 1 is composite by showing that it is divisible by the number 641. 641 can be written as 16 plus 625. And we all know that 16 can be written as 2 power 4. And 625 can be written as 5 power 4. Let us take this as equation number 1. Also, see the number 641. It can be written as 640 plus 1. And it can be written as 5 into 128 plus 1. And 128 can be written as 2 power 7. So, this also, that statement can be rewrite as 641 is equal to 5 into 2 power 7 plus 1, which denoted by equation number 2. Now, we can consider the number 2 power 32, which can be written as 32 can be written as 4 plus 28. So, using the formula a power mn is equal to a power m plus a power m into a power n, we can write this 2 power 32 as 2 power 4 into 2 power 28. And using the equation number 1, 2 power 4 is nothing but 641 minus 5 power 4 into 2 power 28. That is using equation number 1. Now, we can multiply these two numbers. We get 641 into 2 power 28 minus 5 power 4 into 2 power 28. This 641 is the into 2 power 28 is a multiple of 641. So it is denoted by m of 641. So again, we replace the 2 power 28 as 2 power 7 the whole power 4. So in next step, these can be written as m of 641 minus 5 into 2 power 7 the whole power 4. Now, again using the equation 2, this line can be rewrite as m of 641 minus 641 minus 1 the whole power 4. So if we expand using the algebraic equation, that is a minus b the whole power 4, we definitely get m 641 in the all the three terms, the last term will be 1. So we can write this as m of 641 minus m of 641 plus 1. That is first term and second terms are containing m of 6, that is 641, that is they are multiple of 641. So we can take 641 outside. So there will be some constant. So this can be written as m of 641 minus 1. So we can take the minus 1, negative 1 to the left side. So we get 2 power 32 plus 1 is equal to m of 641. That is multiple of 641. That is Fi is multiple of 641. That is it can be written as the product of two numbers. That is its actual value is 641 into 6700417. So from this we can observe that this Fi has more than two devices. That is one Fi 641 6,70,417. So Fermat's conjecture failed to be true for n is equal to 5. And also in the year 1880, Landry proved that F6 was composite by establishing the integer 274177 as a factor of F6. So Fermat's conjecture failed when n equal to 6 also. So though no general proof is known to confirm that F1 fails to be prime for all n greater than or equal to 5, it is believed like that. That is Fn is not prime number. That is the Fermat conjecture is failed after n greater than or equal to 5. For example, there are if we give particular values of n, like that if n is greater than or equal to 5 or 16, 18, 21, 23, etc. up to 1945, Fn are found to be composite. So the largest Fermat's composite number known so far is F 1945. This number has 10 power 528 digits. Now we will see Fermat numbers. So the numbers Fn equal to 2 power n plus 1 for n greater than or equal to 0 are called Fermat numbers. We have verified that F0, F1, F2, F3 and F4 are prime numbers, and F5 and F6, that is greater than 5, are composite numbers. No Fermat prime corresponding to n greater than or equal to 5 has been found so far. If at all there exist any more Fermat primes, it has been proved that number of Fermat prime is finite. Now we have some special property regarding this Fermat numbers. That is Fermat numbers are relatively prime. Now we will see what are relatively prime numbers. If any two numbers having GCD only 1, then they are called the relatively prime numbers. Sometimes they are said to be co-primes. Now let us prove any two Fermat numbers are relatively prime numbers. For that we are considering two Fermat numbers Fm and Fn, where m is not equal to n, m and n are any natural numbers. Now we have to prove that GCD, it is denoted by open interval Fm, Fn, which is equal to 1 for all m not equal to n. So first we know that any two natural numbers have a gap. So by using principle of mathematical induction, so using that principle without loss of generality, we can assume that m is greater than n, so that m is equal to n plus k, where k is any positive integers. Now we are replacing m by n plus k. So let that GCD of Fn plus k, Fn as d. Now we are going to prove that this d is 1. Then we are through. So now consider the equation Fn plus k minus 2 divided by Fn. So now using the definition Fn, this Fn plus k is nothing but 2 power n plus k plus 1 minus 2 divided by 2 power n. And this 2 power plus 1 minus 2 will be get cancelled and we will get minus 1. So 2 power n plus k minus 1, and we can apply the 2 power n plus k as 2 power n into 2 power k. So we get the relation as Fn plus k minus 2 divided by Fn as 2 power n into 2 power k minus 1. So this term can be written as the right hand side term, that is numerator in the right hand side term can be rewrite as 2 power n the whole power 2 power k minus 1 divided by 2 power 2 power n plus 1. Now take the 2 power 2 power n as x. So the above term will be written as fn plus k minus 2 divided by fn is equal to x power 2 power k minus 1 by x plus 1. We have very well aware of the binomial expansion, that is x power n minus 1 can be written as x power n minus 1 minus x power n minus 2 plus and so on into x plus 1. So in numerator we will have x plus 1 into x power 2 power k minus 1 minus x power 2 power k minus 2 and so on minus 1 divided by x plus 1. So in next step x plus 1 will get cancelled. So we will get the term as x power 2 power k minus 1 minus x power 2 power k minus 2 plus x power 2 power k minus 3 and so on minus 1, which is an integer. Why it is an integer? Because we observe that the x is in the form 2 power 2 power n. It is a natural number. So if you add natural numbers, we again get an integer, maybe positive or negative. So f power n plus k minus 2 divided by fn is an integer. So if we divide that fn plus k minus 2 by fn, we get an integer. That means the remainder is 0. That is the number fn fully divide, that is fn plus k minus 2. Now we know that the GCD of fn and fn plus k is d. That means d is a common divisor of fn and fn plus k. That is, it divides fn and also divides fn plus k. So this gives us d divides fn and d divides fn plus k. Now we have proved that fn divides fn plus k minus 2. Now we know that d divides fn plus k and also fn are even numbers. So it can divide 2 also. So d divides fn plus k minus 2. Now we can combine these two. That is, d divides fn and fn divides fn plus k minus 2. Hence we can conclude that d divides fn plus k minus 2 and also d divides fn plus k. And there is a property for that divisibility. That is, if d divides a and d divides b, then d divides a plus b. So here we are having the fact that d divides fn plus k minus 2 and d divides fn plus k. So that d divides fn plus k minus 2 plus or minus fn plus k. So fn plus k, it will get cancelled. We will get d divides 2. So we all know that 2 is a prime number. Its only divisors are 1 and 2. So d divides 2. So the only possibility is d is either 1 or 2. Since fn are all odd numbers. Why they are all numbers? Because it is of the form 2 power 2 power n plus 1. The 2 power 2 power n is an even number. We are adding 1 with it. So it is an odd number. So odd number never has 2 as a divisor. So d has only possibility 1. So the GCD of fn and fn plus k is 1. So from this up to this I am concluding this module. So in this module we will discuss about many more conjectures regarding the distribution of primes, and Fermat conjecture is failed for up to 1945. It is true only for n equal to 4, and from that conjecture we are given the Fermat numbers and we concluded that Fermat numbers are relatively prime.